SQL injection presentation. Give it up.
Hi everybody, I'm Cameron Hotchkies. I'm here from hex90.org and I'd like to thank you for coming. It's the hardcore of DEF CON that shows up to the last talk on the Sunday. Some people were coming in with their luggage, so that's pretty awesome. So thanks to you guys for showing up. I'm going to be talking about automating blind SQL exploitation. So not going to focus on detecting blind SQL injections, more on getting the goodies from a blind SQL injection. So we're going to start off pretty basic. Start off with what is a SQL injection. Hopefully most of you have encountered the term at least before. Comes down to pretty much just one thing. It's client-supplied data, and it's passed to a web application, and it's not appropriately validated for bad stuff. And once this stuff goes on, because it wasn't validated, it goes on to be processed by commands by the database, and that's when you have your fun. SQL injection, every type of SQL injection you're probably going to encounter can be used to do one of a couple things, which comes down to performing operations on the database. So when I say that, I mean you could use it to bypass authentication mechanisms. You could use it to read information that you probably shouldn't have privileges to, and people are assuming you don't have privileges to, but you do. And writing information to the database, such as new accounts or bogus data, stuff that's really going to mess up the DBA and make him cry in his sleep. So SQL injection comes down to roughly three main forms, breaking things down as we go along. The first form, it's three main forms, is when you're reading information you're not supposed to get. And that's what we're going to be focusing on. That's what I mean by when we go on to exploit it. So the first method is redirection and reshaping of the query. That's where the web application's displaying stuff in tables, and you can reshape the query to dump everything beautifully formatted for you, print it out, show your friends. It's like, look at this, they even formatted it nicely. Usually you'll need to know some of the schema to go about doing that, but if you're lucky you can dump the schema in the tables and go from there. The second method, and the method a lot of people are familiar with, is the error-based injection, and that's predominantly in Microsoft SQL Server. You'll put in a SQL query that's poorly formed. It'll create an error message, and through the error message you can reverse engineer the query that it was called with, then reverse engineer the schema of the database, and then start to pull out the actual information by forming bogus queries that says, oh, I can't convert the password to an integer because the password's not an integer, but it displays the password right there for you. And the third method, the method we're going to be using for the rest of this talk, is blind injection. Now, when I say blind injection, there's a couple different definitions of that as well, so I'm just going to focus on the one that I mean. And when I say blind injection, I mean you can pass data to the web application, and it's still going to pass information back to you, but it's going to pass it very, very subtly. It's simply going to be able to respond to yes or no questions. So you send in a question to the database, and it responds somehow, and it says the answer is yes. But the problem is that any form of SQL injection can result in significant data leakage or data modification attacks. So it's not that it's better or worse than another type of injection. They all have the same end result, which is the person running the web application getting screwed. So with blind attacks, we're playing 20 questions with the web server. I'm sure everybody's played 20 questions when they were younger. It's like, are you a mineral? Yes. Are you a tank? Excellent. But why focus on blind SQL injections? Well, the thing is, blind is just as common as almost any other form of SQL injection out there. And in fact, even the other SQL injections can be treated as blind if you'd want to. Most of the time you wouldn't want to because you actually want the information now. But the other problem with blind is that blind involves a false sense of security on the host. The $4 an hour Visual Basic programmer who put up that web application, who heard of SQL injection once in some class, decided, oh, there's error messages, they're bad, I'll hide them from everybody, and then I'm okay. He's not. So there's a false sense of security going on where they think they're safe, yet they're still just as vulnerable, except through a slightly modified attack. The big problem with blind SQL injections, though, the part of people who still are aware of them, they don't take them as seriously because they take far too long to perform manually. It's a large investment of time, and it's very time-consuming, tedious, painful to actually implement them. Has anybody in the room here actually performed a blind SQL injection by hand before? All right, about what I'm thinking. So at Hex 90, we decided this was a pain in the ass, so we're going to write a tool to do it for us because we're really, really lazy up there. So we figured we needed an automated tool because we know we're playing 20 questions, but the reason we stopped playing 20 questions when we were 4 was the fact that it's really, really boring. But we can ask as many as we want. We don't have to stop at 20, it's just keep on asking. As long as we have questions, the database will still answer as long as we haven't DOSed it to oblivion. But if we want the username of the database, say it's a SQL Server database, and they changed the username away from SA. They did something right. So we want to find out what the first letter of the username actually is. Well, that's going to take 7 requests back and forth to the web server. But if there's 8 characters in this username they're using, that's going to be 56 requests in total. 8 times 56, it's not that hard. But to find out that it was an 8-letter username in the first place, that's another 6 requests to the web server, just asking yes or no questions. So we're already at 62 questions for the username. The username really doesn't do us any good. It was just sort of, oh, I wonder what it is. So we're at 62 requests, and that's already starting to add up. So a fairly conservative estimate is typing this into a web browser. This is going to take about 10 seconds per query to the web server. And assuming you don't make any mistakes, you haven't had too much coffee while you're doing it, then you're already looking at over 10 minutes just to get that 8-character username sitting there at your computer. It's like, and the username's value is greater than whatever. It's like very, very painful to do. But as I said, the username isn't our goal. Probably you're not going to run off to your friends like, I got the username. You're going to want to go and you're going to want to get the schema. You're going to want to get the entire database. You're going to want to get basically the gold that's locked in the database. So if you want to perform a non-trivial penetration off of a web application, you're going to want the table names, you're going to want the column names, you're going to want the data types of the columns, you're going to want the actual data stored in the database, and all of a sudden you've gone from 10 minutes to hours or days or months, possibly years, depending on the size of the database. Now, writing a tool might sound simple, but for an effective and comprehensive tool, I can assure you it is slightly more complex than a few shell scripts in netcat. Now, I've got a couple examples for you to ease the boredom here. This is Bob's Bike Shop. Probably the ugliest web application you've ever seen. We designed it as well. We were focusing more on the tool though. But it's got everything that a web application vaguely should have. It's got a pretty banner at the top. It's got a menu along the side where you can choose different types of stuff you're going to buy. It's got an ugly green table that shows you the bike information that you're looking at. Apparently the Schwinn bike that this customer was looking at is going for $30, so these guys are going out of business. But it's got everything that a standard web application might have, including a SQL injection. So if you probably can't see it, hopefully you can notice that it changed a little there. Watch the address bar, grows a little. What I've appended onto that is simply and 1 equals 1. 1 equals 1 is true. It's a fairly straightforward logical statement. So it didn't change the page after we added that to the product ID field in the address bar. That's a very simplistic basic building block of a blind SQL injection there, because we've asked it what a true is and it returned the same page. Now if we change the 1 equals 1 in the address bar to 1 equals 0, it's telling us it couldn't find any information anymore. So it's safe to assume at this point that we've got the product ID field there is directly sent to the database where it says send us all the bikes where the product ID is equal to, in this case 2, and then this is where we append our extra logical statement and 1 is equal to 0. Well, so it sends back all the bikes where the product ID is 2, when 1 is equal to 0, it never sends anything back. We've got a false statement, therefore we know that the database is sending us back Boolean values of true and false. I'm going to take a little sidestep here for a minute. And when I was talking about getting the username, it takes 7 requests and 8 requests. I wasn't pulling those numbers out of my ass. There's actually a method to it. And what we do is you can convert anything in the SQL Server to an integer. And what you do in this case is, once you've converted it to an integer, it's very easy to pull it down just using logical statements. You can create a recursive routine to select a range, start off maybe at 0, nice middle area, and then increase the value, start off, increase it by 2, increase it by 4, increase it by 8, until you find a value that's higher than the integer you're dealing with. Once you found that range, basically the last one you stopped at and the previous one before, you start cutting that in half and exponentially drop it until you've zeroed in on the actual integer you're searching for. And what you can do if it's not an integer that you're actually searching for, if it's a character, search for the ASCII value. That's an integer. If it's a binary field, you can convert each element to the ASCII value and then grab that number. If it's a date, you can convert it to text, which then goes to ASCII, which is an integer. Everything can be converted to an integer and pulled out, albeit slowly, can be pulled out through this method. So now that we know we can pull the information out of the web server, we found the hole, we figured out how we're going to go about pulling all the data, we just have one more problem. And that's, how do we recognize a true page and a false page from the web server? Well, for us, it was pretty simple. For a true page, there was an ugly green table with an undervalued bike and a price there. And for the false page, it just said no rows found. You can spot it like that. But the problem is, a computer can't do it as easily. There might be other stuff going on. It just sees a collection of ASCII values. So it's a bit harder for the pattern recognition to take place. It's not that complex to understand that the computer doesn't see things we do. We're pretty much used to that. So the big thing is, a lot of people want to just do a straight string comparison. You've got the true page, you've got the false page, and then just copy those strings, compare the strings. If they're equal, then move on with that. But web applications aren't getting less complex, they're getting more complex. Everybody wants to show off, everybody wants to add extra bells and whistles. So there's going to be more dynamic content as web applications go around. You might find a lot of web applications currently you could just do a string compare on, but it's growing really, really quickly, the fact that there's going to be extra stuff going on. There's going to be an increasing chance that the dynamic content on the page is unrelated to the actual dynamic content you're viewing. So there's a lot of extra stuff going on. The string comparison might work for something along the lines of an error-based injection, but where you've got constant strings you can sort of target in on, but not for a blind injection such as this. Back to the false page that I showed you earlier. If you look right above the no rows found, if you're in the back, it looks like a gray bar. It's basically a date. And it's including the time, so that means that section is changing every second. So every time you do a query, you've got a little bar that's changing. We can see that and immediately dismiss it as a date, doesn't matter. But it's going to be something that's changing in terms of the overall string. Then underneath the no rows found, it's telling you what page you requested. Now that seems a bit contrived, but if you've ever gone to a news site or any site where somebody wants you to refer it to a friend, well, the refer it to a friend is just a link to the URL you requested, and if you're injecting over the GET request, then that's going to change every time that you hit the site as well. So, first possible solution for dealing with the true pages versus the false pages versus the pages you want to know whether they're true or they're false is use an MD5 sum. Take an MD5 of the true, take an MD5 of the false, then the unknown, and which one's the closest. Well, as I said earlier, over and over, web applications are designed to be dynamic. There's going to be a lot of extra stuff going on. And the way MD5 was designed, it's a message digest, which means it was designed to highlight small changes by making large changes in the actual sum. So, take a look at this. Took the home page of Google, very, very simple page, and I saved it, took the MD5 sum of it, then I changed the title tag, changed it from Google to Hoogle, increased the ASCII value of the entire thing just by 1. And this is a different MD5 sum. So the original is the blue, the changed one is the red. It only changed by 1 character, which went up by 1 value, and they're nothing similar. You can't even tell where they changed. It should be at point 2. I know that because I did it, but The numbers don't even line up to the actual lines because an MD5 sum is always going to be the same size. So overall, we know that MD5 sums can't handle the changes well for something like this where there's going to be small incremental changes that we want to sort of filter out, and we don't really care about them. And it might work for the same applications where the straight string comparison might work, but it's not going to be comprehensive. And if the string comparison worked, then why bother with the extra time with the MD5? So another possible solution would be to parse the actual HTML into a tree data structure. You go on and you represent the HTML entities as nodes in the data structure, and you look for differences in the shape of the tree. You write recursive traversal algorithms. But a couple problems with that, and the first one is I'm lazy. That's a bit more complex than what I wanted to do when I was writing a tool. But a big problem with it is that if non-markup data is changing, then it's not going to change the shape of the tree. If it's just the textual content, which is altogether possible, it happens somewhat regularly, then you're going to have to find a different way to figure out what's going on in the actual nodes of the tree. And the other thing is it's easier to implement an XHTML parser than a realistic HTML parser. By that I mean that auto-generated crap that front page spewed out for years and years and years, and the auto-generated crap that lots of people still write through their web applications, the kind of stuff where it's just chunks and chunks and chunks, and to actually read it, if you had to fix it for some reason, you're like pulling out your hair. It's just as bad to go through and parse with a tree data structure. So the third solution, the one I actually ended up using, was linear representation of ASCII sums. Now, what I mean by that is take the HTML file that you get for each response and delimit it by carriage returns. So you basically split it up by lines, take the ASCII sum of each character in the lines, and so now you have a single value for each line in the HTML file. From here, it's just one array that you can work with. And because of the magnitude of the sums that you're dealing with, small changes by like 1 or 2 characters aren't going to make that much of a difference. This is the same graph of Google versus Hoogle that I showed you earlier with the MD5 sums. It's line section 2 down there, that you can't even see it just because you're dealing with the closest range is 20,000. That's the notch there. So a change of 1 isn't going to show up too much. So we figured out how we're going to get the signatures. We still have to do comparisons, figure out how we can recognize the trues versus the falses, since we found a way to represent them. And to do this, we're going to need base cases. You do this initially anyways when you're trying to figure out and learn the web application. So you can find a true page versus a false page at this point. You always know that 1 is going to be equal to 1. I can guarantee that to you. And you know that 1 is never going to be equal to 0, hopefully. And so once you do this, you use known true pages, known false pages, and you found a base set of cases to work with for your HTML comparisons. So from Bob's Bike Shop, the web app I showed you earlier, this is the true page versus a false page compared on a graph with the linear representation of the ASCII sums. So the blue, you can see it follows the same as the brown as it starts. At about 10, that's where the difference takes place, where the no rows found versus the green table shows up. So the green table takes up more space on the blue, and then it eventually tails off and finishes the same way that the brown does because it has a single line and is a bit shorter. Just in case you think that was a bit too contrived, this is a realistic signature. This is a real commercial web application that's somewhere out on the web that has a blind SQL injection. I don't remember which page I took this from, so don't ask me after the talk. But it's still vulnerable as far as I know. So I said earlier that this linear representation, small changes in the input means small changes in the output, but the fact is there are still small changes in the output, so you can't do a straight up comparison. So when these changes take place, such as the time changing by 1, increasing the value in very small increments, it's going to make very, very minor changes that we would sort of ignore, and we can actually use a tolerance instead of a straight comparison for comparing these values. If you've done any numerical analysis, you know you never use equals, you always use a subtraction for a tolerance. You do the same thing here. So you just take the sum of the known, minus sum of the unknown, take the absolute value, toss it over the sum of the known, and if that value is equal to your preset tolerance or less than your preset tolerance, then you treat it as an equivalency. Oops. There we go. And this is the same thing with the tolerance bands, just sort of illustrating what I meant by it. You can see that as it starts off, they're in the same tolerance because they are the exact same, but once it gets to the parts where it's supposed to diverge, the tolerance at this point isn't enough to create a false negative or a false positive. It would be a false positive. And so there's no problems with that, but it still allows for minor changes. The tolerance shown here is about 10%. If you're ever doing this on your own, I wouldn't recommend anything higher than 0.01%, or you're going to get a lot of false positives on that one. The realistic one I showed you would trip up if it was higher than 0.01%. So tolerance works for the most part. It'll work a good chunk of the time, but there's better ways to go about it. It does extra calculations, comparisons it doesn't really need to be doing, and it doesn't take advantage of stuff that is known to be bogus data we don't care about. So we decided to create a filter to the data that we're dealing with. On the left is the Bob Spikes true signature. You've seen it on graph. Now this is the array form. And on the right is the false page. Know that because it's a bit shorter. And if we identify every element between the two that are in the same position, that are equivalent to each other, then we know that those values have nothing to do with the injection. They have nothing to do with the actual information being presented to us. So if they're the same at this point, they should be the same at every other point, and we know they don't matter to what we're doing. So get rid of them. At this point, we've halved the data that we're comparing against each other. And this saves us a bit of time. This page is really small. In a larger page, it cuts out an even larger chunk. But why stop there? There's still extra stuff we know is crap. We know will trip up our web application. The stuff we filter out by eye. Think of the time or the referral to a friend. We want to still get rid of that. So we have a second filter we apply. And this allows the application we're attacking to be profiled a little bit more before we go on to proceed with the actual attack. So we want to remove the junk data that's going to screw up the results. The only thing is we have to get more than the initial set of base cases. But really overall, we're going to be doing thousands and thousands and thousands of queries against the web server. An extra 5 really isn't going to hurt it too much. If it is, then your attack wasn't going to happen anyways. So we've already applied the subtractive filter to these two, and they're supposed to be 2 true pages. All we've asked is 1 is equal to 1, which is true. Is 2 equal to 2? Yes, it is. So the pages should be the same because it's the same answer. But they aren't. So anything that's changed over this 2 queries, and we ask a couple more just to be sure, anything that's changed at this point, we know this has nothing to do with our injection. This is changing on its own, and it's going to come back to bite us later. So get rid of it now. Don't even look at it later because it will screw us up. So we clear that out, and what we do is we save in memory which elements of the signature that are actually used for the comparison. So it's like hit element 12, hit element 13, hit element 14. If that's what we're looking for, then we know it's a good signature. Otherwise, we assume it's a false. So the benefits of using the second filter is at this point, we're pretty sure we can get rid of the tolerance. You don't have to if you're not 100% on it, but I've been pretty comfortable not using that tolerance anymore when I've been doing my comparisons. Works out pretty safely. At this point, if something doesn't exactly line up, that means I have to readjust my filters and move on from there. And it will remove a large portion of the dynamic content that's unrelated to the actual injection we're performing. So this is the part where I introduce Squeal. Squeal is a tool that we created. I've been presenting how Squeal actually works here, and we created it to perform blind SQL exploitation automatically for us. We wrote it in C#. I wrote it in C# in Linux, which annoys some people, but it works for in Windows and Linux. If you want to use Linux, get Mono 1.0 or later. Mono's become pretty stable recently. But there's a Windows.Forms version for Win32 and the GTK Sharp version. They should both be on the CD, but I haven't had a chance to look yet. And it's free for non-commercial use, free for educational if you're presenting it to people. Check out what I can do with this. And the fun stuff is any data you pull through Squeal, it'll save to XML. So it's very easy for you to read. You don't need Squeal to work with the data again later. You can just print it out and view it any way you want. So here's a sort of example of the XML that Squeal uses. This looks like the actual signature of the attack that we'd use. So it's got the target address, the method that you're using, whether you're using SSL. There's some extra parameters that might get stored there depending on if you're using them or not. Every parameter that's required for the injection, whether or not it's the injection point. And every time once you initialize, which is gathering your base cases, then it will actually save the signature sets for you. So you only have to do that once and you can play again later. And here is the actual tool. This is the Windows version, pretty Windows XP version. And basically what you would do is you select the type of injection, which is the only choice you have is blind, so that's a pretty easy choice right now. And enter the target URL right around here. Running at localhost test just because we're going to show you a demo shortly. And choose whether you want to do a post or a get, whether you want to use SSL. If you want to comment at the end of the query, Squeal only runs for SQL Server at the moment, so that just means it's appending a dash to the end. And this is fun over here. This is for people who want to send it through a proxy. If you want to do this anonymously, don't know why you'd want to do that, because nobody would want to be anonymous while running this, but it's fun stuff. And once you filled out that information, go on to enter the information about the actual parameters, the stuff that goes after the question mark usually, or if it's a post, any of the stuff that's being returned. So you enter the name, the default value, whether or not it's injectable. If it's a string injection you're doing, simply put the closing tick on the end and it'll recognize the apostrophe and work with it from there. You also have the option to add HTTP headers, aka cookies. So if you have to squeeze by authentication with your own cookies, you can do that. And once you've got that set up, you click the initialize injection and it gathers your base cases. Once you've done all that, it only takes about a second to gather the base cases, unless you're running through a really slow proxy. You can move on to do stuff like grab the username, takes a couple seconds, comes back, we're running as SA. Did anyone see a problem with that? No? All right. But yeah, SA. Then once you've got that, you don't even need the username. That's one of those curiosity things. It doesn't help you. You don't use it later. Since you're just asking yes or no questions, you don't have to authenticate. They've already done that for you, those friendly web app coders. But you can load the table information, and that means the name, the ID stored internally, the number of records, in each table. Once you've got the table information, load the field information. And for the customers table, I've already done this for you. It takes a little bit longer than what I'd like it to take right here. It takes about 5 to 10 minutes to grab all this information, but it's better than doing it by hand, so you can go make yourself a coffee while it's doing it. So we know we've got the fields customer number, customer name, customer address, customer phone, customer fax, customer CC number. Fun stuff. What are we going to do with this? So, we want their name. We want this CC number. Don't know what that might be. And we want to save it. So, and we start downloading. Now it's not instantaneous because you're doing a ton of queries right now. So we'll go back to the slides. So what it does when it gathers the table information, this is just basically batch store procedures. So if you've done this by hand, you know this by heart right now, and this is probably the last thing you want to see. But what SQL does is it goes through and it gathers the ID numbers for every table. It wants the numerical ID numbers because those are easier to work with and they're already integers for us. So start off, get the count, which is the number of tables in the database. It's a fairly small integer, go up, down, find it. Then you want the smallest ID. Go up, down, find it. Then you work through, get the next smallest, next smallest, next smallest, until you found all the IDs in the table. So once you've grabbed the table IDs, which means you don't have to worry about apostrophes getting filtered out anymore, because you're not working with strings, you're working with numbers, you get the length of the name matching that ID. Then you get each ASCII value. You just basically choose the ASCII value for the first letter, the second letter, third letter, and work your way through until you've got the entire table name. And all that information is saved. Gathering the field information, it's very, very similar. You get the number of columns that are in each table, which you reference by the table ID you already got. Once you found these, you get the column number. Now, unlike the table IDs, which are long integers, so don't use 32-bit integers because it will crash on you. You're going to want a long integer that's fairly weird. The column IDs are different. For SQL Server at least, they start at 1, they end up whatever the last column is. It's always sequential, it's just an ordering internally. So really you could probably guess, but this is just for completeness sake. So once you've got the ID numbers, which it does reference it by, do the same thing to grab the length of the name, grab each character in the name. Then once you've done that, you're going to want the data type because that's going to change how you're pulling the information from the database later. Because an integer you just grab. If it's a text string, you grab the ASCII value. Otherwise, convert to text, then grab the ASCII value. Then convert back when you've got it. So the X type is the data type that they actually mean when they reference the columns, and which is stored conveniently for us as an integer. And this is taken from MSDE, just pulled it out by hand earlier, and save you guys some time if you want to work on something like this later. These are just the numerical values that match up to each data type that you probably encounter. Okay, running time. It looks like it's done, so we will go to Fun Explorer, and where did I put it? That's embarrassing. My documents. Not even my laptop. This looks like it. So hopefully you guys can see that from the back. Can everybody see that? This is the information we pulled out from the database. Looks like I'm a victim of my own blind SQL injection here, but I'm not alone. Some people should have known better than to buy from Bob's Bike Shop. That's not really DT's credit card number, so you can stop writing over there. But it basically pulls all the information out. It stores it in XML. It'll store it with the primary key from the table, whether or not you asked for it, because it needed it to grab it anyways. So if you need to work with it later when you're messing around and decide to change somebody's expiry date on them for fun. So back to PowerPoint and running time. So to grab all the information I showed you, grab the username that was there. There was only 2 characters to grab the table names, the table contents, the field information, plus just those 4 records. That's already over 2,700 HTTP requests to the server. If you use the 10-second rule we talked about earlier that I claim is fairly conservative, this would have taken over 7.5 hours non-stop. That's not a work day. That means not stopping to play Quake. That means not stopping to get coffee. That's 7.5 hours non-stop. So who was it that said that they'd done this by hand before? All the way through? What size t-shirt do you guys have? Where? Extra large? Medium? Okay. I don't know if they're pulling one over on me, but I'm feeling generous. Extra large? Bear with the, I can't find anything. And slowing me down, I'll find yours afterwards. It's a nice fancy internet villain t-shirt. Hex 90 gear represent. But yeah, so in reality, that would have taken 7.5 hours to do by hand. In reality, it's going to take a lot longer. In a real production database, it's going to be more than 4 records you're pulling down, hopefully, otherwise you're wasting your time attacking them. I mean, testing against them. We're all good guys here. So, nothing's perfect. I don't claim to be, and I don't claim the tool is. There are still problems with SQL as it stands right now. The first big problem is noise generation and server log denial of service. When you're doing thousands and thousands and thousands of requests against your web server, chances are they're going to notice at some point just this string of SQL statements in their logs. If they don't, then whew, good admin, but chances are they're going to notice. And if it's a big database, there's a chance that you might fill up their hard drive before you pull out all the information from the database, because they might have decided, oh yeah, 100 megs is enough for the web server, but I need a 5 gig database. Falls apart. Also, if it's a very small web server, experimentally we've kind of noticed that it can knock out the web server for a second or two, resulting in a real denial of service, so run this on your own systems. The other problem is, it has issues at the moment with if there's no carriage returns in the auto-generated HTML. That means the guy who wrote it didn't think of putting in the carriage return or the carriage return character, so that means if you were to view it by hand, it's just one long string. I'm sure everybody's seen one long string. Yeah, nobody likes to work with that, not even SQL. But there's ways to possibly get around that too. So one of the first options that people immediately think of is, why not just force the carriage return after a certain number of characters? But if you've got random stuff changing in length as well, then all of a sudden your signatures are going to be offset, and it doesn't seem to make much sense anymore because they don't match up, the filters don't work anymore because things are shifting because of that one forced carriage return, and it throws off the comparison techniques. At this point, you need an HTML parser of some kind. It might be the tree parser I discussed earlier. Another option would be to run something along the lines of HTML tidy. You'd have to double check to make sure it's deterministic, which means I'm going to be double checking to make sure it's deterministic. Make sure the same thing comes out every time, and at that point, it's filtered out and cleaned up so that SQL can read it and work from there. Or an option that was suggested at Black Hat was to, instead of doing something along those, instead of always delimiting by carriage returns, give the users the options to delimit by other characters, which is something that we're looking at rolling into the next version. So, where do we go from here? Well, same techniques could be utilized in other types of applications that still interpret results from HTML responses. So as long as you're trying to read values, read like information subtly from what comes back, you can use a similar signature set to work from there and filter it out similarly. Even if it's more than 2, you can just filter out the 3 and do comparisons along the 3 or more. But you guys want to know fun stuff, right? So we know that we've been able to automate blind SQL injection, which means we've been able to automate the process of putting stuff on and reading stuff off of the SQL server. So, fun stuff, SQL IRC. Yay! Could be idle, could be lag, nobody's really sure, but everybody loves IRC, so why not implement it that way? Another possible option that could be used for something like this is SQL FTP. And if you guys can't read the almost Linus Torvalds quote there, that means only wimps use take backup. Real men just upload their important stuff to somebody else's SQL server. Something else you could possibly do. I don't know if you can even see that. SQL Quake. No, that wouldn't work. But if you missed Johnny Long's talk, not really sure where you might be able to find sites because you just want to test, but you want to find stuff and you want to play around. Where would you go about finding sites you could play around with that are possibly injectable? Well, I'm going to break it to you. Nobody's going to email you randomly out of the blue. Just doesn't happen in this day and age. Nobody's going to email you unsolicited. It's not going to be a stranger that emails you. You know the guy that's emailing you. And they're not going to email you with random stuff that you don't care about. And if they do email you, they're not going to email you a SQL injection. Yeah, I'm not joking. But then again, if they did email you, and they did email you a SQL injection, it's not like they're the kind of people that want to remain anonymous and don't want to be tracked down. So, just closing up here, a couple suggested papers that if you don't have a lot of experience with SQL injection yet and you're looking at learning more about it, the first 2 are from NGS Systems by Chris Anley. Very good papers, both related to SQL Server, primarily the error-based stuff. The third one is the blind SQL injection paper from Spy Dynamics by Kevin Spett. Another very good paper detailing the processes that I was talking about automating here. And the fourth one is another one on blind SQL injection from Imperva. I don't have the actual link to it at the moment, but it's easy to find off of imperva.com. They take a couple different approaches than the Spy Dynamics guys do, so you might want to check that out. So I'm going to open it up to questions right now. If you're looking for this tool, it's not up yet. It should be on the CD. It will be available at this website. There's a couple other tools that are available there as well. So does anybody have any questions? I see you. At the moment, we just took SQL Server because we were kind of short on time, and most of the examples are for that. But as long as you have access to the equivalent of the sysobjects table or read access to the schema, you should be able to do it. We're looking at trying to figure out how to do it with Oracle, although Oracle DBAs are usually a bit better about locking down their systems than SQL Server DBAs. So as long as there is a sysobjects table that you can get access to, there's a way to exploit it that way. The question is, do I have any experience attacking Java applications in terms of SQL injections? I don't, myself. I basically pick on the weak, which is the ASP coders out there. Do you have any? But I'm told it's doable by people who know more than I do. Is there a specific question related to it? Basically, as far as languages go, you're going to find that as long as a language supports parameterized queries, that's the big thing. If you're looking at locking down a database, make sure you're using parameterized queries, and if you have the option to use stored procedures, that's another layer that makes it more complex for the attacker to get through. And chances are that if they're not targeting you specifically, they're just going to move on because it's not worth their time. But parameterized queries, I can't stress this enough. .NET has it, Java has it, later versions of PHP should have it, and if you're not using it, you really should be. If the language you're using isn't using it, find a different one. There's a lot of ones to choose from at the moment. Unfortunately, a lot of textbooks out there tend to start off with, this is your database code, create it on the fly, there you go. And they're teaching bad examples right off the bat, and even really good books are still doing bad examples for SQL connections right off the bat, and it's not till 3 chapters later where you stop reading at this point that it gets into safer database calls. So look for parameterized queries of some kind or another where you actually identify the name of each element that you're hitting and the data type that it's going to. Is there any more questions? Yes. The question was, can you insert a delay to the web server? The current version of SQL doesn't support throttling as far as the delay. I believe that's what you're asking. It could be done. Yeah, sort of having it pause before it does the next one and pause before it does the next one. The current version doesn't do this. That's something I'm looking at putting into the next version because of that other denial of service problem that happened. So the next version will have that, but currently it doesn't support it right now. It's just simply that it just fires them off as fast as it can. So it's about 3 or 4 per second, I think, it fires it off right now. Yes. You can only stop in between where the buttons are in this version. So it's like you can load the tables, load the table information, and then stop that, come back, load the field information, come back. So the general answer to what you wanted was no, I think. Oh, you basically, well, you have to grab all the table names at once, but you just grab the fields for each table as you need it. So then you can just grab the specific information you need. Is there any more questions? It's a binary search. Because all the integer searches that take place are binary searches. Because even for an alphabet, you're looking at 14 at the maximum for a binary search, I believe. Whereas if you do it by a non-binary search, it's going to be longer than 14 on average. So it's faster for, even if it's just an alphabet with a limited range, you're still going to want to do a binary search. I think the only difference with that is that we know the top and the end point, or we start between 0 and 255 and then go from there for ASCII values when we're doing it that way. Any more questions? Well, thanks everybody for sticking around. My name's Cameron Hotchkies.